Okay, fitting a trend line and forecasting. Last lesson we talked about seasonal variation and how if you have data that is seasonally variable, and I know people are writing stuff down, but I'll just flip back here quickly. This was our seasonal variation. If you have data that varies seasonally, like the green one does, then this can be hard to make predictions from or hard to apply. But if we deseasonalize that data, then we get something that's more predictable and therefore can be regressed, or we can build a linear regression of that data. We can extrapolate with that linear regression, and then we can re-seasonalize the data to make predictions for each season as is appropriate. So we talked a bit about seasonalizing, etc. I believe I'm about to be interrupted. Okay. So we did just get interrupted. This is going to be a bit of a weird video. So we've got seasonal variation, and we can deseasonalize, build a linear regression of that seasonal variation, predict into the future, and then reseasonalize to get some information. This is the foundation of many complex unfamiliar questions because there's quite a lot of procedural work behind it. When you extrapolate to make predictions for the future and then reseasonalize, this is, my OneNote's not working, sorry. This is called forecasting. Hence why the title is fitting a trend line and forecasting. But before we do the seasonalized data, we're going to talk about just forecasting for very simple data. So here's an example. I don't know a lot about what the example is. It says year and students. So it could be something like the number of schools in Queensland each year from 2008 through to 2017. I've stolen this graph straight from the textbook, so it's in your textbook, and there's an example associated. This is a fairly linear trend, which means that we could build a linear regression of this trend. So we've done, in Chapter 2, a lot of work on bivariate data, and you've just done a PSMT on that. And in that bivariate data unit, you talked about linear regression, you talked about building the least squared regression, y equals a plus bx. This is time series data, but it's time series is just a specific type of bivariate data. So if we've got a decent linear trend, we can build a linear regression, which is what we're going to do here. So first of all, hopefully you haven't forgotten this, but recall that we have a linear regression in this form, y equals a plus bx, slope and gradient are calculated there, and we've also got these definitional things that we will use in this topic. And hopefully you can build in various different forms linear regressions and also correlation coefficients to talk about that regression and the strength of the regression given different information, maybe data, or you might actually be given SX or SY, you might be able to use your calculator, you might not, etc. So here's an example, and I've deliberately chosen this example to talk about a couple of things. So Daniel, who's somebody, I don't know who, records his phone charge 6 times across a day. There's my graph, and that's his phone charge from about 7 a.m. through to about 2:10, give or take. Now, a couple of things, first of all. Time series produce time scales, and time scales can be a bit weird. They're not all decimal. So you have to remember a few things, which I'll talk more about a little bit later in the OneNote. But for now, if you want to convert 923, that is not 9.23 hours. And this is a really common mistake. 923 is actually 9 hours and 23/60ths of the next hour, because there's 60 minutes in an hour. So that would make it 9.383. She's S5. That took me a while. Okay, so 923 I've written here is awkward. 9.383 is fun or nicer, and it fits on our graph better. So just be really wary that the minutes and the seconds in any time scale are measured in groups of 60, not groups of 100. So you might have to do that conversion, otherwise you'll find that you are out a little bit. In an exam, it's quite unforgiving. We'll know if you do this wrong, input data in your calculator wrong, and then calculate a correlation coefficient or a least squared regression, you will get almost the right answer, but you won't get the right answer. In an external exam, they will say, here's the answer students will get if they use minutes incorrectly, and they'll have it there, and there'll be a mark or two deducted. So make sure that you get those right. Now, we're told this. R is equal to negative 0.993, so that's pretty good regression. And SXSY, the average X and the average Y. So we're using X and Y, but we've got time as our X scale and Y as our charge. Determine the linear regression Y equals A plus BX. Interpret the slope concept. And when will Daniel's phone be flat? They're the questions we're being asked, and this involves a level of forecasting. So how do we determine the linear regression, first of all, in the form Y equals A plus BX? Can you recall those equations for me? We determine B first. B is something like R times, which one is it? SY over SX. And so that's what? 0.993 out here, 0.993 times, it's negative 0.993 because it's a negative value there, 24.08 over 2.698. No, that's fine, I'll do it. Don't worry about it. Negative 0.993 times 24.08 over 2.698. That is negative 8.86. And A, what's A equal to? Mean of Y, take away B times the mean of X, yeah? Where am I at? I've lost. There we go. So Y bar minus B X bar, which is equal to 62.33 minus negative 8.86 times 11.05. 62. Minus my answer times 11.05. 160.26, etc. So therefore, Y is equal to 160.26 minus 8.86x. Question B, which I might do predominantly verbally, says interpret the slope B and the intercept A. So the slope is negative 8.86. What does that mean? That again, sir? Now just go back to the context for me. Excellent. So every hour, my battery or this Daniel's battery is decreasing by 8.86%. Okay, that's first. So B, the percentage per hour lost equals 8.86. We expect that to be negative, so it makes sense. In terms of reasonableness, this is a reasonable solution, and it's going to last 8.86 goes into 100 about 12 times. So we're pretty happy it's going to last for the day. What about A? A is the intercept. 160.26. What does A represent? No problems. What does A represent? It represents intercept. Does this make sense for this to be the intercept, 160? Doesn't make sense for this to be the intercept. Why is it okay that that is the intercept? So in this case, Brad, probably you could be a little bit more mature. In this case, 160 does not fit the context. You can't have 160% full battery, but we started recording, so I'm assuming here that Daniel has taken his phone off the charger at 7 a.m. but our time is starting at 0. So the 160 comes from at time equals 0, it's 160, but really our model doesn't start till 7. So the effective domain of our model is from 7 until flat. Outside of that domain, it doesn't make sense. Just to show you what I mean here, I go from 100 and my linear regression goes through here. I can't also have negative percentage. So the phone just goes flat at some point. Beyond there, my model doesn't make sense. Above here, my model doesn't make sense.
Really sorry, Mr. Mann.
Just gone, yeah. Oh, if anybody watches this video, it's going to be the worst video ever. Just terrible. Okay. Any questions on that? So you always have, every time you do a forecasting question, you have to take a step back and consider the domain, consider the reasonableness of your A and B. They probably make sense, but probably not initially. So I'm just going to make some notes here quickly. A is 160. Only reasonable at 100% at 7 a.m. And question C, when will Daniel's phone be flat? How do I answer that question? Any takers? See what you've made me do? So what's that mean? 0%? Yeah, okay, let's flat at 0%. And Y or X is 0. Y, so this is our Y value. So we get 0 equals 160.26 minus 8.86X, which means that X is equal to 160.26 over 8.86. And that is 18.09. It's what I get. Now, it does say phone flat. So this is the reverse of what we talked about earlier. 18 means 6 o'clock at night, but not 9 minutes past 6. So be really careful here. I get this. So this is 18 hours plus 0.09 times 60 minutes. So I get that decimal now multiplied by 60. That will give me the number of minutes. Should be less than the 9 that we might have. On my calculator, subtract the 18, and then I multiply that by 60, and I get 5.3 minutes. That is 6:05 in the evening, so it's PM. Phone only lasted 11 hours, which is problematic, but I'll let him deal with that. Any questions on that? To question C, then you've forecasted. It's another word for extrapolating. So hopefully that's not too hard for you. There's some notes on forecasting, and then we're going to do the chicken farm question, and then I'm going to leave you for today. So was A plus BX, A is intercept, B is a slope, Y is a response variable, X is explanatory variable. We're talking about time here. It's a time series type question, but you can obviously predict in the future or extrapolate bivariate data that isn't based on time. It's just not called forecasting. Forecasting is a specific term for time-based data. We forecast means we're predicting something will happen in the future, which is that time-based thing. So here's Joanna. Joanna owns a chicken farm. She collects eggs, but allows some to remain and hopefully increase her chicken population. Probably should have written that as, yeah, well, obviously some of the eggs remaining won't increase the population, but this would be a good model for a chicken farm. She's determined that her daily egg collection can be predicted by the following regression. So there's the following regression. What's the slope of this regression? 0.7. Is 0.7 a good thing or a bad thing? Put your hand up if you think it's good. We'll call it 1 in total. I've got 2 halves. Put your hand up if you think it's bad. I've got 3 halves. That's 1 against 1.5. Put your hand up if you don't know anything about chickens and aren't willing to. You've now voted 1.5 times. I think it's a good thing because it's positive. So positive slope represents growth. We don't know how good it is. Maybe in the chicken farming industry, you really need to have growth of more like 2 or 3 or something like that. But for now, it's positive, it represents growth. In the last question, the slope was negative, which represented decay. It was the battery was going flat. In this context, growth is good. That's what she's trying to achieve, and there's growth here. What does the 228 represent? The what's it? The y-intercept. And so in terms of the context, what does that mean? 0 days, she would have how many chickens? 228. So this intercept represents that she started with 228 chickens. That's what it represents. So you've got to be able to read a question and pull that stuff straight off. This is simple familiar at its best. Classic simple familiar. There's the context. How many chickens did she start with? 228. It's a 10-second question, worth a mark in the exam. Should be simple familiar. So say that again. Oh, number of eggs. Sorry, not number of chickens. Correct him on that. Sorry. Anyway, there we go. 228 eggs. 0.7 is her eggs. The number of eggs she's getting per day is growing. It's data. You don't get 0.7 of an egg, but it's built from data. So obviously her data would be a little bit more sporadic, but hopefully it follows this. Forecast the number of eggs that Joanna will collect on the 23rd of March. So here's my question for you. How many days from the 1st of January is the 23rd of March? And I'm going to give you 1 minute to do this now. And then I'm going to put up 4 options on the board now. So the class has guessed 82. If I asked for the 2nd of January, if it said, forecast the number of eggs Joanna will collect on the 2nd of January, you'd put X equals 1 in, wouldn't you? Because the 2nd of January is 1 day after the 1st of January. So 82 days after the 1st of January is actually the 24th of March. So be a little, and to be honest, in most cases, they'd probably still give you the credit. But be a little bit careful with time, particularly calendar time. If the 1st of January is the first day, well then 1 day after the 1st of January is the 2nd. So you're actually out of sync by 1. So in this case, the 23rd of March is the 82nd day in a year. It's 81 days after the 1st of January. Does that sound all right? Okay, so just be wary, be careful, and the best way to deal with that is think, what number would I put in for the next day? What is the next day? 2nd of January, I'm putting a 1 in. So to answer this one, I won't do it in light blue. I get y equals 228 plus 0.7 times 81, and 22 plus 0.7 times 81 is equal to 284.7, and I'm going to do this. I'm going to say 284.7, I'm going to put down my calculator answer, and then I'm going to put down a rounded answer because this is discrete data. And I would expect you to put both of those down. There might be credit for both of them. So make sure you consider, can I get 284.7 of an egg? No, I can't. And both. Is that all right with everybody? And it's just rounding it appropriately. Interpret the slope and intercept. We've kind of done this already. 228 is the intercept, and it's the number of eggs initially, and 0.6 is the slope, and it's the growth rate, which I'll shorten to GR, of eggs per day. 0.7 eggs per day. So with these questions, I would anticipate that most of you will find it really, really easy to do the linear function stuff, substitute in and build an answer, but make sure that you can interpret as well. Interpret will come up almost certainly somewhere in one of your exams, so make sure that you can do it. Any questions?